Hello students, welcome to Spectra Education Academy. In this video, I am going to explain answers for short answer type questions from the chapter Moving Charges and Magnetism. Let us continue with the first question. State and explain Biot-Savart law. So first let us write statement. Statement is magnetic field induction due to a small element of the conductor. Magnetic field induction or magnetic field strength, magnetic field induction due to a small element of the current carrying conductor current carrying conductor at a point so you have to understand like this. So let us say this is current carrying conductor. Let us say this is the portion of length dl. So throughout the total length you are choosing a small element whose length is dl. So total conductor as well as this element are carrying current I. Now you are choosing a point P here. So at a point P, this point P and length element dl can be connected by a line. So definitely there will be some angle between the line joining the point and element. So this is theta, you call it as. So keeping all things in mind, the magnetic field induction due to a small element of the current carrying conductor at a point, that is dB. Magnetic field induction is dB. So more is the strength of the current through the element as well as through the conductor. More will be the field strength at that point. Let us call this the first equation. So in words, how can you write this? Magnetic field induction is directly proportional to magnetic field induction is directly proportional to strength of the current. So at that point, so this is first one. So you can see the equation and you can understand the sentence. Second one is dB directly proportional to dl. So what is dl? Length of the element is directly proportional to dB. It means more is the length of the element of the conductor, more will be the field at that point. So therefore, magnetic field induction is directly proportional to length of the element. So it means this one. More is the length of the element, more will be the field at that point. More is the strength of the current, first one. More is the strength of the current, more will be the field at that point. And third one. Let us write dB directly proportional to sine theta, which means magnetic field induction is directly proportional to sine of the angle. Magnetic field induction is directly proportional to sine of the angle between the position vector and the element. So what is the position vector? Position vector is this. Sine of the angle between position vector and element dl. So you can see this equation, you can understand. This is third, you call it as. So this is second. And this one is first. So last one. Fourth one will be dB inversely proportional to square of the distance between the point and the element. So magnetic field inwards, magnetic field induction is inversely proportional to square of the distance. Square of the distance. So this square of the distance between the point and the element. Between the point and the element. So it means more is the square of the distance, less will be the field strength at the point. More is the angle between the position vector and element, more will be the field at the given point. More will be the length of the element, more will be the field at the observed point. And more is the strength of the more will be the field at the observed point. So collecting all these four, you can write that dB directly proportional to I dl and sin theta inversely proportional to square of the distance. On removal of proportionality, you will get mu naught by 4 pi I dl sin theta divided by r square. So in vector form also you can express this because magnetic field at a given point is a vector quantity. dB is equal to mu naught by 4 pi I dl, unit vector we can write, divided by r square. So therefore, cross product between two vectors, unit vector and dl. So you all know that unit vector can be expressed as vector by its magnitude. So in such case, you can write that mu naught by 4 pi I dl with in place of r cap, you can write that r bar by. Already there is r square, there is one more r mod. So keeping this in mind, we can write that mu naught by 4 pi I dl cross r divided by r cube. So this is how you need to represent the answer. Now let us continue with the next question. It's a numerical. A current of 10 ampere passes through two very long wires held parallel to each other and they are separated by a distance of 1 meter. What is the force per unit length between them? So simple numerical, this is question number 2. So formula will be mu naught by 4 pi I1 and I2 L by R. So therefore, so mu naught by 2 pi, because simple formula will be, this will be F is equal to I into L into B. Magnetic field due to straight conductor will be, suppose let us say force on the first one carrying current I1, this is falling in the field 2. So therefore what you can write is I1 L mu naught I by 2 pi R. So therefore this can be I2 mu naught I1 I2 L by 2 pi R. So you know that mu naught is 4 pi into 10 to the power of minus 7. In the question I1 is given 10, I2 is also 10, then L divided by 2 into pi. Distance between the two conductors is 1 meter. So you can understand that this is the first conductor, this is the second conductor. So both are carrying 10 amperes of current, and the separation between these two conductors is 1 meter. So therefore, you can find out the force per unit length, F by L is equal to, so you can cancel. This is 2 and 2, then 1 meter. Then you can cancel, this is 2 zeros with minus 5 will remain with So force per unit length will be 2 into 10 to the power of minus 5 Newton per meter. So this is the answer for the question. Moving to the next question. A long, question number 3. A long straight wire carrying current 35 amperes. What is the magnitude of the field at a point 20 centimeter from the wire? So understand that this is the wire. You are here at a point at a distance of 20 centimeters. You can say under the wire. So 20 centimeters, centi means minus 2 meters. So this is carrying current of 35 amperes. So directly we can use from Ampere circuital law, B equal to mu naught I by 2 pi. Actually this is BDL is equal to mu naught times the current. On simplifying this, you will finally get this one. So B equal to mu naught is just now you have done one question 10 to the power of minus 7, that is mu naught. Current is 35 amperes divided by 2 pi. How much is R? 20 centimeters. So 20 into 10 to the power of minus 2. So you can say that this is 2 pi, 2 times get cancelled. Then next what you can do is this is minus 5. Then this can be 10 times. So 35 by 10 means 3.5. So magnetic field at 20 centimeters will be 3.5 into 10 to the power of minus 5. So magnetic field unit is Tesla. Okay. Yeah. So let us continue because this particular question is based on application of Ampere circuital law. Let us first finish Ampere circuital law. I'll come back to fourth question afterwards. Yeah. Let us continue with the question. State and explain Ampere circuital law. So let us say this is a closed path. Let us say you can say it can be clock closed path. So you can draw on a table this one. So any arbitrary shape you can take. Assume that few currents are enclosed by this closed path. Let us say currents into the plane of the closed path. You can consider this is positive. Let us say I1. So currents going into the plane of the paper, which are perpendicular, and currents going out of the plane of the paper. You can say this is negative. If you consider this is positive, this can be negative. Take a few more currents. Let us say one more current. This is I3 going into the plane of paper. Again, you take negative. This is negative. This is going into the plane of paper, negative. Going out of the plane of the paper, which is perpendicular, positive. Again, you take I4. I4 out of the plane of the paper, you take into. It is again positive. So out is positive. In is negative, you take. Out is positive. Out is positive. In is negative. So it means this intos are inwards. Intos are inwards. Dots circle outwards. So now you can write the statement. Magnetic field index, the line integral of magnetic field induction around any closed path is directly proportional to or is equal to mu naught times the net current enclosed, mu naught times the net current enclosed by the closed path. So it means mathematically you can understand that this is line integral BDL is equal to, you mentioned that this is line integral of magnetic field induction around any closed path. This is all. is equal to mu naught times the net current enclosed by the closed path. So this is mu naught I net. So how do you find out I net? So let us say I1, comma I2, comma I3, you call it as I1 and I3 are the currents out, going out, going out, and which are perpendicular to plane of the paper. Plane of the paper. So take them as positive. Similarly, I2 and I4 are the currents going inwards and perpendicular to plane of the paper. So you take them as negative. So what is the net current is? So net current is both I2 and I4 are negative. I1, I2, I3 is again positive. I4 is negative. So therefore this is called as net current. So you can refresh the statement as B dot dl is equal to mu naught I1 minus I2 plus I3 minus I4. So this is what the desired answer. Thank you very much, students. In my next video, I'll continue the answers for question number 4, 6 and 7. Thank you very much, but don't forget to share and subscribe with your friends and relatives.